Hello friends. So, we have seen the finite element modeling using triangular elements, and we discussed different elements. I mean 3 noded triangular element that has the constant strain state, constant derivative condition, and then we also discussed 6 noded triangle that will have a linear derivative field. So, it is also known as popularly known as linear strain triangle or LST. And then if we need to have cubic variation within for the primary variable within element boundary, then we can have 10 noded triangle with one I mean 9 nodes on the edge of the triangle and 1 node in the interior of the triangle. And we also discussed how the interpolation functions for these triangular elements can be very easily derived by using local coordinate concept of local coordinates, which are related to the partition of the area with of any point with coordinate x y in the interior of the domain, and how the one point defines or divides the entire area of the triangle into different parts, 3 parts, and those ratios of the area with respect to the total triangular total area of the triangle, that defines the value of the local coordinate system, local coordinate, particular local coordinate for nodes 1, 2, 3 for 3 noded triangle. And this is taken to as a standard definition. Local coordinate varies from 0 to 1 as parallel grid lines being parallel to the element edges, and then each point within the interior within the domain of the triangle can be defined by an ordered pair of these 3 local coordinates L1, L2, L3, and with using that using this local coordinate system, it is very easy to derive the interpolation function for higher order elements, quadratic elements or cubic elements. But triangular elements, they are simplest 2 dimensional element covering area, but it is possible to cover a larger amount of area in one element by using rectangular geometry. So, that is the next element that we will discuss, 2 dimensional element. In 3 dimensional analog, the analog of triangular elements is a pyramid tetrahedron, and the analog of a rectangular element in 3 dimensional domains is a cuboid, and also in between we have prism or a triangular prism. So, all of them enclose area, and they can be used for deriving the finite element models. So, we now discuss the development of a rectangular element and see how the interpolation functions are defined for rectangular elements, because all that changes in the entire process of finite element analysis is the discretization using the element appropriate element, and then defining the interpolation functions, how the primary variables are approximated within the element, within individual element. So, rest of the process, rest of the steps of entire finite element analysis, they are identical and they follow naturally after this. So, we consider rectangular element, and there are 2 elements actually in the family. So, rectangular finite elements, the first element is of course 4 noded rectangle. So, 4 vertices, node 1, node 2, node 3, node 4, right. So, if I have coordinate system somewhere, let us say x and y, and I can have this line as x is equal to minus 1, this line as x is equal to plus 1, and this line as y is equal to minus 1, and this line as y is equal to plus 1. So, these are the grid lines, so to say. So, you can see that the location of the nodes is at the intersection of the grid lines. So, this is the grid line for x is equal to minus 1, this is the grid line for x is equal to plus 1, this is the grid line for y is equal to minus 1, this is the grid line for y is equal to plus 1, and intersection of these grid lines is what defines the location of nodes of define vertices of this rectangular element, and this is the element domain omega e. Now, the equation of lines, these lines, this particular line is defined by x plus 1 is equal to 0. This particular line is defined by equation x minus 1 is equal to 0. This particular line is defined by y plus 1 is equal to 0, and this particular line is defined by y minus 1 is equal to 0. And in this we have the clue to derive the interpolation functions. The requirement for the interpolation function is that interpolation function for ith node should evaluate to unity at the corresponding node, and it should vanish at all other nodes. And if the nodes are located at the intersection of the grid lines, the simplest way to achieve vanishing condition of the interpolation function is to just multiply by appropriate grid lines. So, for example, if I am trying to derive the interpolation function corresponding to node 1, all that I need to do is take the equation of line 2 3, multiply it with equation of line 3 4, and it takes care of the condition that n 1 should vanish at 2, 3 and 4, right. And then I evaluate that product at the coordinates of node 1 and normalize with respect to that. So, that is the normalizing condition, and that makes the interpolation function for node 1 evaluate to unity, and that is essentially what we call as Lagrange's interpolation. But in this case we are essentially talking about Lagrange's interpolation is defined for one dimension. So, essentially Lagrange's interpolation for node I is given by product of j is equal to 1 and I is not equal to j, x minus x j divided by x I minus x j. So, essentially equation of line zeros of individual grid lines. So, x is equal to x j, and the equation of that grid line would be x minus x j is equal to 0. So, I multiply with that and normalize it with that particular expression evaluated at the node I, x is equal to x I, and then take the product. Now, this is pth degree polynomial. So, whatever number of terms we will have, p number of products. So, it will be pth degree polynomial, and together this is a variation with respect to x. So, in case of 2 dimensional elements, all that I need to do, I will have similar kind of expression for y. So, product j is equal to 1 and I is not equal to j, y minus y j divided by y I minus y j. So, interpolation function for node 1 would be given by n 1 x x y actually would be given by x minus 1 equation of this line, that is x minus 1, right. So, x minus 1 multiplied by equation of this line 3 and 4 joining the nodes 3 and 4. So, that is equation y minus 1, and I evaluate this at node 1 which has coordinates of minus 1 minus 1. So, that would be minus 1 is minus 2, minus 1 is minus 2. So, minus 2 multiplied by minus 2, that is 4. So, that simply becomes 4. So, this becomes the interpolation function for node 1. Similarly, interpolation function for node 2 as a function of x and y is simply product of equation of line 1 4 and equation of line 3 4 normalized to have unit value at node 2. And what are those equations? X plus 1 and y minus 1 divided by, I evaluate it at node 2. Node 2 coordinates are 1 and minus 1. So, node 1 coordinates are minus 1, node 2 coordinates are 1 and minus 1, node 3 coordinates are 1 1, node 4 coordinates are minus 1 1, right. So, when I evaluate it at node 2, so x value is equal to plus 1, y value is equal to minus 1. So, 2 multiplied by minus 2. So, this is equal to 1 plus x 1 minus y divided by 4. And similarly, extending this, we can have interpolation function for third node. So, for third node I need to multiply equation of line 1 2 and equation of line 1 4, and that would be 1 plus x multiplied by 1 plus y and divided by this numerator evaluated at node 3, and node 3 coordinates are x is equal to 1 and y is equal to 1. So, that evaluates to 2 multiplied by 2. So, 4, and finally, we can have n 4 x y, that is given by equation of line 2 3 multiplied by equation of line 1 2. So, that is equal to 1 plus x multiplied by this would be 1 minus x. Equation of line 2 3 is 1 minus x and equation of line 1 2 is 1 plus y, and when I evaluate it at x is equal to minus 1 and y is equal to plus 1, which are the coordinates of node 4, I get 2 multiplied by 2, that is equal to 4. So, these are the 4 equations, 4 interpolation functions which define the variation u within the element x y is equal to n 1 u 1 plus n 2 u 2 plus n 3 u 3 plus n 4 u 4. And similarly, the displacement in y direction v is given by n 1 v 1 plus n 2 v 2 plus n 3 V 3 plus n 4 V 4. So, collectively I can refer to this as n 1 0 0 n 1, then n 2 0 0 n 2. I am collecting all the terms, both of these equations, writing in the same expression. U 1 V 1 U 2 V 2 U 3 V 3 U 4 V 4. So, essentially we can write this as n u I. N is a matrix of shape functions. So, n 1 is a function of x y within the element domain omega e, and for node 1 and node 2, similarly node 2, node 3, node 4, and these are the nodal values of the primary variables u 1 and v 1, displacement along x and y directions, and together they give us the desired approximation for primary variable, variation of primary variable within the element u as a function of x and y. And once we have this substitution, we have this variation, we can go back to the weak form and work out the domain integral evaluation, and those from that point onwards it is essentially exactly the same process. It is an integral in 2 dimension, and the expression is available as a variable in 2 dimensions, and x y, though integrals can be evaluated, it is a very regular geometry x and y and Cartesian coordinate, and integrals can be evaluated easily. And the domain integral, again domain integral would go in opposite, in the counterclockwise direction. So, for domain integral, so this is the unit normal for each side, and again as discussed in the case of triangular elements, these domain boundary integrals in the boundary term of the weak form needs to be evaluated only when the element boundary coincides with the boundary of the problem, because in this interior, if any of these element boundaries in the interior of the problem domain, then the outward positive normal, the direction of the fluxes, secondary variable, they would cancel out by virtue of equilibrium, and these boundary terms need not be evaluated. And when we are evaluating these at the boundary term, this 2 dimensional can be converted into 1 dimensional integral by similar kind of mapping process. X y coordinate system can be converted into a local ST coordinate system, such that one of the coordinate directions aligns with the edge of the boundary that is being considered, and origin being located at one of the nodes, so that the other coordinate direction takes the value of 0, and this problem, the problem becomes simple 1 dimensional integral, and those can be evaluated analytically. So, that is the basic definition for triangular elements. So, the 4 noded triangular element is the simplest, 4 noded rectangular element is the simplest rectangular element that we have, and as I said, there are 2 families of rectangular elements. I did not take the names of those families, because first element 4 noded rectangular element is common to both the families, but the 2 families of rectangular elements are Lagrange family, and second one is known as Serendipity family. Now, the difference between them, geometry is of course rectangle, right. So, whether it is from Lagrange family or from Serendipity family, we are looking at rectangular elements. So, both of them are rectangular elements. So, what is the difference? Difference is in the construction of interpolation functions. In Lagrange family, we consider the placement of nodes at the intersection of the grid lines, so that the interpolation functions are very easily derived by using product of Lagrangian interpolation functions in respective directions. So, I take the Lagrangian interpolation along x, I take multiply it with the Lagrangian interpolation of desired degree along y direction, and then normalize it with respect to whatever node we are looking at, and we have the desired interpolation function, very straightforward. And that way we can generate any degree of polynomial, any higher degree elements does not really pose much of a challenge. It is only finding out, we have standard way of defining Lagrange interpolation formula, and we can just knowing the position of the nodes, in the knowing the coordinates of the nodes, we can simply find out what is the equation, what are the Lagrange interpolation in x direction, and multiply it with the Lagrange interpolation in y direction, and that is the interpolation function for that node, and of course, normalized that will be normalized to have unit value at that node. Serendipity family is little different in the sense that it comes, the name serendipity comes from a place called Serendip, where the prince of Serendip was known for accidental discoveries. So, he never went out to discover or intentionally tried to find something, but he had that knack. It is said that he had that knack that he would stumble upon something useful. So, serendipity family rectangular elements were developed somewhat like that. The interpolation function, they were often a matter of trial and error. You would keep on trying and trying and trying, and suddenly you hit a golden pot and you find the set of functions which satisfy the desired requirement. So, that is how serendipity family originally was derived and the name got stuck, but now we of course have a very systematic way of developing interpolation functions even for serendipity family. So, let us take, I mean, the first element 4 noded rectangle is common to both of them. So, we now go to the next degree of accuracy, that is second degree quadratic variation. So, the polynomial variation within the element has a quadratic variation. So, one thing that we need to look at, as we discussed about this triangular elements, there was always a 1 to 1 mapping. So, in Pascal triangle, right. So, in Pascal triangle, for 4 nodes we need these terms. For triangle we only need one x and y. So, linear term complete. So, complete polynomial. So, this is 0, here it is 1, this is 2, this is third degree, this is fourth degree. right. So, for triangular elements, 3 noded triangular elements, we only needed 3 terms. So, it was a polynomial approximation was complete in first degree, there was no extra term. But while using the rectangular elements, although a rectangular element, we could define a larger geometry which would otherwise have taken 2 elements, 2 triangular elements to cover the same area. So, there is some kind of economy in the number of elements to be processed, because it takes a substantial amount of computational time to derive the element level equilibrium equations, to compute the element level equilibrium equations. So, if I can do the work of 2 elements by using one element, that is a considerable saving, right. So, that way rectangular elements are more efficient, but it comes at a cost of an additional term from the second degree polynomial x y. So, the approximations are all based on 4 terms, 4 noded rectangle, they will have 4 terms in approximation, and those 4 terms will involve one constant term, one linear term in x, one linear term in y, and then a product term x y that comes from the second degree. But the convergence rate would still be governed by the first degree, that is the complete polynomial, degree of complete polynomial in the approximation. So, this is a little bit of problem, but not a very serious one. And before going into the details of how do we develop the general principles of developing the interpolation models for Lagrange's family and Serendipity family, let us we also look at what are the requirements. I mean how do they satisfy the requirements of the approximation, how does it satisfy the requirements for the convergence of finite element solution. For the convergence of finite element solution, we mentioned that requirements for convergence. So, that is rigid body modes, and second one is constant strain state. So, constant strain state we have been talking about. If we have this constant terms, I mean linear terms included in the approximation, they will have that value of derivative, constant derivative condition. So, if the problem is such that the first derivative is constant, then if as long as we retain these first degree polynomial terms in the approximation, that capacity is built into the solution, built into the approximate solution, and that constant derivative condition will be represented, right. But how do we represent the rigid body motion? So, for rigid body motion, what is required? I mean if we look at it, this particular thing, let us say element is required to undergo rigid body motion, and it is now translated so this is let us say u 0, right. So, that means the entire element has translated by constant amount u 0 and without straining. So, every node, so u 1 is moving by u 0 along x direction, and y direction the displacement is 0 for simplicity. So, u 1 the displacement node 1, node 2, node 3, node 4. So, node 1 moved by u 1, node 4 also moved by u 1, u 0, and node 2 moved by u0 and node 3 also moved by u0. So, entire block moves as a rigid body, there is no relative deformation. So, there is no straining in the element. So, if that happens, then this motion should be captured. So, when I say u0, so the displacement, nodal displacement of each of these 4 nodes is same u0. So, u x y is equal to u0 and this should be equal to n multiplied by u0 0, u0 0, u0 0, u0 0. That is the vertical component, the displacement along y direction is 0. So, v at x y is 0. So, that is what we have this v 1 is equal to 0, v 2 is equal to 0, v 3 is equal to 0, v 4 is equal to 0, but all the 4 nodes move in x direction by the same amount u 0, u 0, u 0, u 0. So, essentially this looks like u 0 multiplied by n 1 x y plus n 2 x y plus n 3 x y plus n 4 x y. On the left hand side we have u 0, on the right hand side we have u 0 multiplied by this sum of interpolation functions of all nodes. Now, this rigid body mode can be captured only if this is equal to 1, and this is what we call as partition of unity. So, this is very important test or very important requirement for the interpolations to satisfy. We will explore this more and the rules of Lagrange's family of rectangular elements and serendipity family of rectangular elements in our next lecture. Thank you.